Okay, let's finish this up. It should be pretty quick. This is going to be the foundation of problem set 3, chapter 25. Please get going on this stuff. It's Thursday morning. I looked on mastering just to see if you guys are doing any of this stuff, or you just sleeping these cold days away, or I don't know, maybe you got a 30-page English paper to write. And I don't think anybody had finished problem set 2. That I get. Hopefully you guys have all started. I didn't dig that deep on mastering to see, but lots of that static stuff in problem set 1. I was hoping a little more of you would have completed that already. Not the case. So point is, get going. All right. I got a charge in space, okay? And I don't know. It's 3 microcoulombs. And it's in a field, a uniform field. I don't know what's making the field of 12,000 newtons per coulomb. How much force? This is going to be over here, QE. 3 by 10 to the negative 6 times 1, 2, 3, 4, 1.2 by 10 to the negative 4, oops, dang, coulombs, newtons per coulomb. This is going to be 3.6 by 10 to the negative 10 newtons. I think I got that. Positive 4. Positive 4, that's a negative 2.036 newtons. Pretty typical type of situation. Okay, that's a yawner. Let's talk more about the field. I'll give you a little insight. You're going to get problems that talk about, oh, well, it's a uniform field. Well, what gives? All right? Remember that. Okay? Earth is big and honking. All right? And the field looks like this, right? And so we see that the further away you go from Earth, the more spread out these lines get. We've talked about that before, and the whole 1 over r squared deal. If I zoom in, because first semester, most of our problems are systems like, hey, we're in the classroom, okay? Let me zoom in a little bit. And yeah, we see, when we're the God's eye perspective right now, the document camera. But if you zoom in right here, you look at these lines and they're like pretty uniform, like right there. Okay? So, same thing could hold true for an electric field. You know, maybe you have the metal dome of a Van de Graaff charged up in the classroom, charged all negative. Okay? And you know that if you put your hand close, you're going to get a gazouche because the field is strong. Remember gazouche, John Travoltage? And if you put your hand back here, you're not going to get zapped by the Van de Graaff. So you know the field weakens, and we know that because we see these lines, okay? That said, if you were a little charged pith ball right here, I mean, yeah, if you go 1 to 2 to 3 centimeters away, the field weakens, but you're still pretty dang close to the ball. Watch out, you're going to get shocked, okay? So, you know, what could make a uniform field like that? I don't know. Lots of things could. Okay, maybe it's a blob, but we're just so close that it's just really strong. Hey, this is going to be quick. Speaking of a varying field, we know that this is kind of a bigger picture, okay? So, 2 more things I want to do. Let's say you have a Van de Graaff, big old charge, 50 microcoulombs. That's a pretty big charge, going to give you a pretty big jolt, way bigger than in classroom, or than in the statics lab we did. Okay? And let's find E 40 centimeters away. I'm not going to bother with direction, we're doing just the math. K is 9 billion. Newton meters squared, coulomb squared. Hopefully we can do this in our head. 50 by 10 to the negative 6. Don't forget meters. Yeah, and of course, yeah, we are. I think we're going to be able to do this. 9 by 5 is a 45, and I got 1,000 left upstairs. Okay? This is going to be 0.4 squared is 0.16 meters squared. And this is going to be a Newton meter squared per coulomb. Okay? I'm going to call this about 15. So 45,000 over 15 is 3. Okay? But I think because of that I have to add 2 zeros. So I'm going to be at about 3 and 5 zeros. And you check me on the powers of 10 there, okay? And look, it's newtons per coulomb. Okay, it's 45,000 over 0.16, and I'm just kind of guessing there. Okay? Yeah, that's pretty much it. Okay? Now, the last thing is, we're still talking about force fields, right? So you can have a situation where maybe you have an electron, and maybe it is in a downward pointing uniform field. Okay? No, maybe it's a little pith ball with just a teeny minuscule amount of charge on it. Okay, we're going mechanical. Okay? Little tiny charge, like literally just a few extra electrons. Okay? Which way is it going to be tugged? Well, if the field is down, that tells me a proton, right? By definition, this field shows me the direction a test charge would feel. So this negative charge, let's say it's a pith ball with a few extra electrons, goes like that. But hey, it's a pith ball, so it's got some weight to it. And what you can do is float it in the field. This is what Millikan did with his oil drops. The Millikan oil drop experiment, famous. He took just oil drops, like a few molecules worth of oil, and put, no, not a few molecules, but a really tiny drop of oil, and amassed a small net charge. And based on observations, we can, you know what, now's not the time to get into it. We'll talk more about Millikan in class, but you can pretty much balance. You can float little particles that have small amounts of charge by doing this. And so, if you know any three, you can find the fourth. And that's the mechanical side of this electricity stuff we do. All right, folks, stick a fork in it. We're done for these snow days. I'll see you tomorrow.